Hello everyone, this is Dr. Zach. So today we're going to spend time once again solving optimization problems. We'll also take a second look at the second derivative test to help prove whether you have a relative minimum or maximum at that critical number. So let's continue with optimization. So you use the product rule in order to find the derivative. Next, you found your critical number by setting that derivative equal to 0. Your denominator was never equal to 0, so we didn't have to worry about finding a critical number where your denominator was 0. You stated your domain to be between 0 and infinity, made a table of values which included your critical number and your endpoints, and then made a statement about the largest population of bacteria and the extreme value theorem. So what we'd like to do is next look at the second derivative test. Now this test can be used to determine whether your critical number is a relative min or a relative max over an interval. So if we know that the derivative is equal to 0 and the second derivative is positive, then your f at c, your value at c, must be a relative minimum. If we know that your derivative is 0 and your second derivative at that value is less than 0, then f of c is a relative maximum. This is your second derivative test. If you have a function such that your derivative equals 0 and the second derivative exists on that open interval containing c, then you have a relative minimum when you are concave up, and you have a relative maximum when your function is concave down. But this sometimes doesn't work. If your second derivative equals 0, you do not know if you have a relative minimum or maximum, and you must go back and do the first derivative test to determine if your extreme value is largest or smallest. So for example 1, we're looking for the relative extrema for f of x equals negative 3x to the fifth plus 5x to the third. We're going to find the first derivative. F prime of x is negative 15x to the fourth plus 15x squared. Do some factoring, because you know I love factoring. We'll have negative 15x squared times the quantity x squared minus 1. So that tells us we have x equals plus and minus 1 as the critical numbers. Now from the critical numbers, we're really interested in if these are relative extrema, minimums or maximums. So if we have f double prime of x, the second derivative is going to be equal to negative 60 x to the third plus 30 x squared. Do some factoring because that just makes life so much better. We have negative 30 x squared times positive 2x minus 1. So when we substitute 1 into your function, f double prime at 1 is going to be less than 0, and f double prime at negative 1 is going to be greater than 0. So we can see that f at 1 is a relative minimum. Oops, sorry, concave up, so relative, concave down, so it's a relative maximum. And f at negative 1 is a relative minimum. Now notice we had another critical number, x equals 0. But when I substitute f double prime of 0, that equals 0. So I really don't have enough information to say if it is a relative minimum or a relative maximum. But looking at the graph, you can see that it is neither a minimum or a maximum. So let's use the second derivative test to figure out where we have relative extrema for f of x. Determining our critical numbers, f prime of x is going to be equal to 2 cosine x minus 2 sine 2x. And then if we determine where this is 0, we might want to use some algebra. We write this as 2 cosine x minus 2 sine x cosine x, but we have to multiply by 2 again. Then do a little bit of factoring. We have 2 cosine x multiplied by 1 minus 2 sine of x. To find the critical numbers, we want to know whether the cosine of x equals 0 and where 1 minus 2 sine of x equals 0 on the given domain. So the critical numbers occur at x equals pi over 2, 3 pi over 2, at x equals pi over 6, and x equals 5 pi over 6. So instead of worrying about where the function's increasing and decreasing, we're going to find the second derivative. The second derivative is going to be equal to negative 2 sine of x minus 4 cosine 2x. And next we'll substitute f double prime at pi over 2 is greater than 0. So the function is concave up, and f of pi over 2 is a relative minimum. F double prime at 3 pi over 2 is greater than 0. So it's concave up again, and that tells us that f at 3 pi over 2 is another relative minimum. Now, f double prime at pi over 6 is less than 0, so the function is concave down, and f at pi over 6 is a relative maximum. We're also going to find that f double prime of 5 pi over 6 is less than 0 and is another relative maximum. So you have 2 relative minimums and 2 relative maximums. All right, so let's talk about example 2. A rectangle is bounded by your x and y axis and by the function y equals 6 minus x divided by 2. So if we sketch a graph of that, we will have, so when you graph your function, you have the y-intercept at 3 and the x-intercept at 6. There we go. Rectangle, there we go, got a rectangle, and it crosses the line at xy. So if you need to rewrite your function, y equals your 3 minus 1/3 x, and then minus 1/2 x, and then we're going to figure out that we want to maximize the area of that rectangle. Notice I chose an arbitrary point, xy, so that the area would be x times y. And if I use my function, y equals 3 minus 1/2 x, to replace the y value, I now have a one variable expression to represent the area. Find the derivative, a prime, and that's going to be 3 minus x. The domain for the x values, think about this carefully, is going to go from 0, less than or equal to x, less than or equal to 6. So the x's are traveling between 0 and 6. So a double prime is very conveniently equal to -1, and the critical number is going to be equal to x equals 3. And a double prime at 3 is also -1. So a of x is concave down on this interval, and a at 3 is a maximum because it's concave down. So this is from the second derivative test. Now, if you want to say it's an absolute maximum, derivative test. Now, if you want to show that you have an absolute maximum, you want to talk about the interval. So, since a of x is concave down on the given interval 0 less than or equal to x less than or equal to 6, the maximum area occurs at x equals 3, y equals 3 over 2. Our third example is going to be a little bit more intense because we are finding the largest isosceles triangle that can be inscribed in a circle of a radius r. So first thing we want to do is draw a circle. And of course, the radius of the circle is r. So we have some points given that that is r. The y-intercepts are 0, r, 0, negative r, r, comma 0, and negative r, comma 0. With that information, we want to now draw an isosceles triangle. So if we want to draw the largest isosceles triangle, let's use 0r as our value, and then we'll draw the triangle to some arbitrary points, x, y. There we go. So this equation for the circle is x squared plus y squared is equal to r squared, and r is some sort of number. We're trying to maximize the area, and I want you to think about the area equation of this circle. Of course, area of a triangle is 1/2 base times height. The base is going to be all the way across this blue line. So that would be x minus negative x, which is 2x. So the base is 2x. Now the height is going to be r minus a value, but I'm not sure which value. The height is actually big R minus the y value, or top minus bottom. So we're going to have 2x times r minus y. Now, when we go back to the constraint equation and solve this for, let's solve it for x. We're going to get x is equal to r squared minus y squared with the square root. All right, do our substitution. We now have the square root of r squared minus y squared times r minus y. Okay, so product rule. Here we go. We have area prime equals, so we have first r squared minus y squared, derivative of the second, plus the second, which is your r minus y, times the derivative of the first. Using that chain rule, 1/2 r squared minus y squared to the negative 1/2 times 2y, and that's negative 2y. Okay, multiply to simplify, because you know you have to find those critical numbers. When you simplify, you're going to get r squared minus y squared times negative 1 plus r minus y times negative y, all divided by your common denominator that you found, r squared minus y squared to the 1/2 power. And then when you set this equal to 0, let's look at those critical numbers. You're going to come up with 2y squared minus big ry minus r squared over that denominator still, r squared minus y squared to the 1/2 power. Do a little bit of factoring. You get 2y plus r times y minus r, almost there, over our denominator, r squared minus y squared to the 1/2. So those critical numbers are going to be y equals negative r over 2 and y equals r. Those are your possibilities. But let's talk about the domain. Back to your picture. We're thinking about the y values. So for your domain, the smallest y value is going to be negative r, smaller than or equal to y is smaller than or equal to big R. So do we really want to use a first derivative test? I don't think so. That derivative does not look friendly. So let's make a table of values. and use the first derivative test, which will give us our x, and when we put in a, substitute in negative r over 2, as well as negative r and r. What do we find? We have zeros, and we also get, when we simplify, a nice little 3r squared over 4, and that is all over a square root. So from the first derivative test, what did we know? We know that the largest isosceles triangle that can be inscribed with the radius of r is going to have an area of root. Okay, so the area is going to be equal to the root 3r squared over 4 times 3r over 2, do your substitution, and that's going to be the largest area by the first derivative test, or the extreme value theorem. Okay, so once again, you're going to be doing some practicing. Questions number 2, give that one a try. Maybe you even want to try number 3. Try those problems and then come back and we will work on example 4. So as promised, we're going to look at example 4. We have an industrial tank that's formed by joining 2 hemispheres to a right circular cylinder. So let's draw the right circular cylinder first. There we go. And then we're going to place some hemispheres on top. All right, now notice you weren't given any equations. You're going to have to throw some labels on. The labels that you know is that you have a radius and a height. Okay, so what we're trying to do here is we're going to take these hemispherical ends. We know that they cost twice as much as the surface area of the sides, and we want to minimize the cost. So minimizing the cost, knowing that the volume is 3,000 cubic feet. So let's piece together a cost equation. Your cost is going to be equal to twice as much of the sides for the hemispherical ends. That surface area of a hemisphere is 4 pi r squared. We're going to multiply that by 2. But then we want the surface area of the sides of the can, and that's going to be 2 pi r h. All right, now we're going to write that volume equation. The volume is going to be equal to your 4/3 pi r squared plus, we have our 2 pi r squared multiplied by h. There's no 2, just pi r squared h. Solving for your heights, after we set it equal to 3,000, you get your 3,000 minus your 4/3 pi r cubed, all divided by pi r squared. Next, we'll substitute the value for h so that we get cost equals your 8 pi r squared plus 2 pi r multiplied by your h value. And after that, we will do just a little bit more simplifying. We end up with a nice little 8 pi r squared plus 6,000 over r minus 8/3 pi r squared. Find the derivative. C prime is going to be equal to 16 pi r minus your 6,000 over r squared, and then minus 16/3 pi. So let's find a common denominator to enable us to find the critical number more easily. And that gives us a 48 pi r cubed minus 18,000 minus 16 pi r cubed over our 3r squared. And when you solve this for r, you get r equals the third root of 1125 over 2 pi, and also r equals 0. Don't forget that one. Okay, so what is the domain of this thing? Look at your h. Your domain So we know that 0 is less than or equal to r is less than or equal to, let h be 0 in this constraint equation, and we're going to have 3,000 divided by pi raised to the 1/3 power. So next we'll draw our table of values. Unless you want to find a second derivative, I'm going to say no to that one. Here's my r, here's my cost equation. We'll place our third root of 1125 and 2 pi, as well as 0 and 3,000 over pi to the 1/3 power. Both of these will give us 0. We like that. And oh my goodness, you can find the cost equation, do that substitution, you end up with a positive value. Now the question says find your dimensions. And the dimensions in here are going to be both r and h. So we will solve, we know r, but then you need to solve for h as well. Make a statement that the cost will be minimized when r equals the third root of 1125 over 2 pi, and h equals, and you better find that from the first derivative test. You have one more question that I want you to give a try. Number 3, finding the volume of the largest right circular cylinder that can be inscribed in your sphere. Give that one a try. Don't spend more than 10 minutes on that problem though. Your assignment for today, you're going to work on page 192 and page 221. All right, so give page 192 and 221 a try, and you have a great day.